Okay, so in this next section of the notes, this is page 2, we're going to talk about the properties of limits as well as how to approximate and estimate limits algebraically. So the first one we have is the sum rule, okay? It kind of goes along with the words that they've given you here, the sum rule. You're going to take two limits and you're going to add them together, which means that their results will also be added together, right? The difference rule, again, we're going to subtract two limits. So, and then that means that their results will also be subtracted. So you take each one individually and then you subtract them from one another. The product rule has to deal with multiplication. You're going to find each limit individually and then you're just going to multiply them by each other. The quotient rule, you're going to take both limits from the top and the bottom, and then you're going to divide them by each other. And then the constant rule, okay, you're going to pull out that constant out in front, take the limit of the function, and then multiply the constant by the function. You can find these in your textbook on page 61, or you feel free to pause the video to have more time to write them all down. Okay, so the first way to approximate limits is going to be substitution. Okay, so a lot of the times you can take the value that they're asking you to be approaching and you can plug it in to that function. Now, again, this only works if the function is defined at that place. So if we look at the limit as r approaches -3, we're going to take -3 and we're going to plug it in to each value of r and solve. So we're going to have -3 cubed plus 3 times -3 squared minus 2r, so 2 times -3 minus 17. Please try to do this without a calculator. There is a calculator and a non-calculator section on the test. So we've got -3 cubed, which gives us -27. -3 squared gives us 9, times 3 gives us 27. -2 times -3 gives us +6, and then minus 17. So the 27s here cancel each other out, and we've got 6 minus 17, which gives us -11. So the limit as r approaches -3 of r cubed plus 3r squared minus 2r minus 17 is equal to -11. If we look at the second example here, we've got the limit as x approaches 0 of tan of x over x. So here, if we just substitute 0 in, we're going to have something undefined. So we need to think a little bit differently. Now this is going to use your trig identities in order to solve this. Now, last year in math analysis, you might have missed the trig identity unit. So if you need a refresher on trig identities, please log back onto Canvas. I will have some old videos there of the trig identities that you can watch because you will need them. So we want to try to rewrite this problem in something that could help us. So tangent, right, if you remember from last year, is y over x, which is sine over x. So we're going to rewrite this as the limit as x approaches 0 of sine of x over cosine of x, right? And now when we divide fractions, right, we take the bottom and we flip it and then we multiply. So multiplied by 1 over x. Okay, so that's the same thing that we have there. We just changed sine or tangent into sine over cosine. All right, so now we could split this up, but then we still have that problem of 1 over x. But remember, we did a graphical problem earlier, right, where it was sine over x. So we can rewrite this as the limit as x approaches 0 of sine of x over x times 1 over cosine of x. Now we can do this because multiplication is commutative, and we still would get sine of x over x cosine of x when we multiplied it out. Now, due to that product property, we can split this up and we can find the limit of the first piece. I apologize for my writing. Struggle with a mouse pad. And we can take the limit of the second piece. So limit as x approaches 0 of 1 over cosine. And now we're going to substitute. So if we plug 0 in for sine of x over x, we know from our previous example that that is equal to 1. All right, if we plug 0 into 1 over cosine, cosine of 0 is equal to 1. Okay, if you need to review your unit circle, please do so. So we've got 1 divided by 1. So 1 times 1 just gives us 1. So the limit as x approaches 0 of tan of x over x is equal to 1. Again, if you need to review your trig and your unit circle, there will be some review notes on Canvas. Please check them out. I do expect you to know that. All right, so the second way is to simplify and substitute. So we're looking at a rational function here. And remember, rational functions may have holes. So we need to check to see if there are holes. So to solve this, we want to factor the top and the bottom as far as we can. And then we want to see if we can cancel anything out, which is where the hole would be. So if we look here, and we're going to take the limit as t approaches 2. The top we're going to factor, so we're going to get t minus 1, t minus 2. And then the bottom, we're going to get t plus 2, t minus 2. Notice we have a t minus 2 in the top and the numerator and in the denominator, so they will cancel. And now we're just going to substitute from here. So we're going to plug 2 into what is left. So we're going to have 2 minus 1 over 2 plus 2. So we'll get 1/4. So the limit as t approaches 2 of t squared minus 3t plus 2 over t squared minus 4 is 1/4. All right, our last one is to graph and approximate. So if our algebra doesn't work, right? So if we factored this like we would have previously, we get x minus 2, x plus 2 over x minus 1, right? And that doesn't cancel, right? So there's nothing, there's no hole here. We plug one in, we get 0, so we can't just straight substitute. So we're going to go and look at the graph. So let's look at our calculator. And we're going to type in x squared minus 4 divided by x minus 1. You could have put this in alpha y equals as well to get the fraction. So then if we hit graph, now again, see my zoom is not super helpful for me. So if I go to zoom and let's look at what the standard one was. This gives you a 10 by 10 square. Okay. So we've got a graph here and we've got a graph here. So it's definitely irrational, right? They've got an asymptote, as you can see here at 1. If you're unsure that that asymptote is there, if you go to the table and look, right, I have an error at 1. So I've got an asymptote there at 1. So it looks like I have a value at 2, 0, 3, 7, negative 1, 3. So these are pieces that I would put on my graph to help me graph it. Now, because I'm on technology, I'm just going to drag the graph over um, onto my screen so that you guys can see it. All right, so if we're looking here, we are wanting to know the value at 1. Now remember, we had an asymptote at 1. In this picture, if you're looking here, right, there is an asymptote here. That was a horrible straight line. Let me try that again. Let me use my straight line tool. So right here through 1, right, we've got an asymptote. So if we look to find a value for where this limit is approaching, again, if we look at the left side, there's nothing there. It's approaching to positive infinity, right? And if we look at the right side of this, it's approaching negative infinity. And we're about to talk about what that means in our next video, right? But if these limits are not approaching the same thing, then the limit does not exist, right? This was approaching infinity. This piece here is approaching negative infinity. So this limit does not exist. Please tune in for the next video for why this does not exist.